Hello! Welcome to Can We Do That Some More, the spin-off where we provide you with questions to try based on the topics that we covered in the videos in my Can We Do That series. Today, following on from looking at using method of differences to find formulas for series with higher powers. And as usual, warning you that we're going beyond what you need to know for the Maths A-level and further Maths A-level qualifications in England, even though we're going to be using skills from those qualifications in order to do what we're doing. And then also on top of that, it's worth noting that the following formulas I'm going to take as assumed knowledge in this video. Some of those may or may not be familiar with you, particularly the r to the power 4 one, if you haven't seen my most recent Can We Do That video. And we're going to be using them as part of what we're doing today. So you might wish to note some of these down so that you can use them for later. So if necessary, pause the video and do that now. But once you've noted those down, these are the questions we're going to be trying to do. Interestingly, that number one question, proving the series for r to the power 3, that's one of the formulas I just showed you on the previous page. But the point is we're going to be proving it, so therefore that's why, although you were given to it on the previous screen, you still have got work to do. And then we're also going to be proving the series formula for r to the power 5. Lots of fun to be had, so if you want, pause the video at this stage and have a go at these questions yourself if you can remember the method that we were using in the last Can We Do That video. Okay, see you in a few moments where I'll go through the questions myself. So let's get on with these questions, starting off with proving the series formula for r to the power 3, and we're going to be using the same method of differences structure we showed in the previous Can We Do That video. Admittedly, that's not the only structure that would work to make method differences find these formulas that we're trying to prove, but this is the most efficient one in my opinion, so that's why I'm using this particular structure. And it's also worth pointing out there's a completely different method you could use to find any of these series formulas that we're trying to prove, which is Faulhaber's formula, which is something I also talked about in the previous Can We Do That video. But that's not the approach we're going to be using for the examples today. If you're interested in me showing a video going through how to interpret Faulhaber's formula, to find these series formulas, then do just let me know in the comments, because I'd happily make another video in the future going through that if you want. But the approach we're using today is this particular method of differences approach that I showed before. So therefore, that approach involved having r plus 1 to the power of 1 higher than the power you are trying to prove the series formula for. So as we're trying to prove the series formula for r to the power 3, we're going to do r plus 1 to the power 4 minus r to that same power, so minus r to the power 4 as well as a result. Because that is something we can do method of differences with. So for instance, if we plug in r equals 1, we'd end up with 1 plus 1, which is equal to 2 to the power 4, minus the 1 to the power 4, we'd end up with r equals 2 being 3 to the power 4 minus 2 to the power 4, r equals 3 being 4 to the power 4 minus 3 to the power 4, and that's enough to already start seeing how these terms are cancelling out, or parts of the terms are cancelling out. We've got the 2 to the power 4, of course, cancelling out with a minus 2 to the power 4. We've got the 3 to the power 4 cancelling out with a minus 3 to the power 4. And although we haven't written the r equals 4 term, we know the 4 to the power 4 part in the r equals 3 term will cancel out with the 4 to the power 4 part of the r equals 4 term. So that's something to bear in mind. And therefore that cancelling will continue all the way down until we get to the r equals nth term. So therefore that will lead to n plus 1 to the power 4 minus n to the power 4. But just like it was above, the minus term for all the terms after r equals 2 are also always being cancelled out with something in the term above. So although we haven't written the r equals n minus 1 term out, it would have an n to the power 4 as part of it, cancelling out the one we've got at the bottom here. That does mean we will just be left with, as a result of calculating this series, the n plus 1 to the power 4 part, and that minus 1 to the power 4 part we had left over from the beginning. But instead of writing 1 to the power 4, of course, 1 to the power 4 is just 1. So I'm just going to take away 1. Nice. Now the reason this is helpful is, of course, as always, we've just written the series formula we're looking at the beginning in the particular way to highlight the method of differences effect that's going on. So we can then see what we're actually calculating by multiplying out some of those brackets. So doing that, we could multiply the r plus 1 to the power 4 using binomial expansion, which would be r to the power 4, 6, no, not 6, he lies, he can't remember his binomial coefficients, I'm very sorry, 4r cubed plus 6r squared plus 4r plus 1, and then we've got the minus r to the power 4 we already had. And of course that's useful because it means a bunch of that stuff's going to cancel out. Well, not a bunch, just one thing. The r to the power 4s are going to cancel out, which is great because it means we're not actually having to deal with the r to the power 4 at all as part of this, because that's not as high a power as we want to be going to. So therefore we have found the series formula for r, or 4r cubed plus 6r squared plus 4r plus 1. And that comes to, as we already found out, n plus 1 to the power 4 minus 1. So what this allows us to do is it allows us to find the series formula for the 4r to the power of 3. So the series formula for 4r to the power of 3 from r equals 1 to n is going to equal that n plus 1 to the power of 4 minus 1 that we had just previously found, minus all those other parts of the series formula we didn't want. So we don't want that 6 lots of r squared series. We don't want that minus 4 lots of r. And we don't want the minus 1 series. Kind of a silly, simple series, but there we go. We're still writing it because it still will contribute to all this stuff. So we could start plugging all the stuff in that we've got so far. So we've got the n plus 1 to the power 4. We can multiply those brackets there. Again, binomial expansion, so just n to the 4 plus 6n cubed. Why, my goodness me, same mistake twice in a row. Thinking too far ahead. So that's a 4n cubed plus 6n squared plus 4n plus 1 minus 1. And then we've got the 3 series formulas to plug in. So 6 lots of series formula for r squared, which is one of the forms I said you could write down from earlier. So that'd be 1/6 n plus 1, 2n plus 1. We've got minus 4 lots of 1/2 n plus 1. And then we've got just minus n on the end. So therefore, I've got to write less stuff out. We could, of course, make the 4n a 3n because of the minus n we got later, and the 1 and the minus 1 cancel out. So already that means we're left with n to the power 4 plus 4n cubed plus 6n squared, but now only 3n, and the 1 and minus 1 are cancelling out. The 6 and 1/6 are cancelling out, so that means we're just left with minus n, if the screen doesn't lag like that. And then I could start multiplying the n and the n plus 1 and 2n plus 1, which would get me 2n squared plus 3n plus 1. And then the 4 and the minus a half, or minus 4.5, will become minus 2, and then we'll have an n squared plus n in there. Multiply out brackets even more. Takes a bit of time, bit of a chore, and that's kind of one of the main problems with this method versus Faulhaber's formula. But there you go. So minus 2n cubed minus 3n squared minus n minus 2n squared minus 2n. Which means that if we now grab all this stuff together, we're going to end up with that n to the power 4 overall. We've got a 4n cubed minus 2n cubed, which will get me 2n cubed, and that's it. So that's just plus 2n cubed. We've got 6n squared minus 3n squared is 3n squared. Take away another 2n squared, leaves me with just 1n squared. And then we've got 3n minus n minus another 2n, so therefore we've got no n's left. So there you go, that is our series formula. That's interesting though, because it means this is the series formula for 4 lots of r cubed, but if you want therefore the series formula for r cubed, it's just going to be that divided by 4, which is therefore 1/4 n to the power of 4 plus 2n cubed plus n squared. But that does indeed, of course, factorize. So if we factorize that out, you're going to end up with a quarter. We can factorize the n squared out of everything. So we end up with n squared plus 2n plus 1. And then what do you know? That quadratic that we've got left also does factorize. So we're going to end up with a quarter n squared, n plus 1 squared. Just like we needed to show. So there you go. That is the first question done. We're now going to use the same approach to find a series formula for r to the power 5, which is going to be very similar as an approach, as an idea, but it's going to sadly involve a lot more multiplying out brackets than it previously did. So we're already mentally prepared for that pain. But there you go. So we're going to do the series from r equals 1 to n of, again, one higher power than what we're trying to find. So as we're trying to find power 5, we've got to do power 6 here. Again, not going to talk through it quite so much this time, but we know there's going to be basically method of differences. Stuff's going to cancel out. You can see it's going to happen. So basically, that stuff that you expect to cancel out is going to cancel out. So I'm not going to bother. Actually, I will. We're right at the nth term. So we've got this, but we know basically that stuff's going to cancel out. We know that stuff's going to cancel out. The 4 will cancel out, even though we haven't written the next term to show it. The minus n to the power 6 will cancel out as well, even though we haven't shown the previous term to show it cancelling out. But we know, therefore, we're going to be left with m plus 1 to the power of 6. Wow, big numbers, minus the 1 to the power of 6, which is just 1. But again, this series that we had at the top could be rewritten as well. It's going to involve multiplying out those brackets as well. So what will we get if we do that? We'll get an r to the power of 6 plus 6 r to the power of 5 plus 15 r to the power of 4 plus 20 r to the power of 3 plus 15 r to the power of 2 plus 6 r to the power of 1 plus 1, and then we still got that minus r to the power of 6 that we had as well. Which means that this is secretly the series formula for just 6r to the power of 5 plus 15r to the power of 4 plus 20 r to the power of 3 plus 15 r to the power of 2 plus 6r plus 1. There you go. So with that, we can now start to rearrange this to get the series formula that we want. So therefore, we're going to end up with 6 lots of the series formula for r to the power of 5 being equal to, big numbers here, but m plus 1 to the power of 6 minus 1 minus 15 lots of the series formula for r to the power of 4 minus 20 lots of the series formula for r to the power of 3 minus 15 lots of the series formula for r to the power of 2. We're just about going to have enough room here. Take away 6 lots of series formula for r, and then minus the series formula for 1. Again, always just that 1 on the end, which makes it nice, I guess. Oh, my pen's disappeared. There you go. Okay, so that means we can now start to deal with all of this, and it is going to be a lot of brackets multiplying out, and it is going to take more than one line of working, which is a shame. Oops, already mucked it up. Multiply out those brackets. Actually, no, you tell you what, I'll leave that until later so I don't have to repeatedly write out those brackets being multiplied out. Otherwise, it will be a lot of effort. It already is going to be a lot of effort, but it'll be even more effort. So the series form for r to the power of 4 is, looking at my own notes, because I can't remember this one off by heart. Actually, I still can. Just there's the number out, the fraction out the front is the bit I can't remember. n plus 1, 2n plus 1, and then it's the quadratic of 3n squared plus 3n minus 1. And then minus 20 lots of 1/4 n squared n plus 1 all squared. I'm not going to fit anything more on this line, so move on to the next line. Minus 15 lots of 1/6 n plus 1, 2n plus 1. And then take away 6 lots of 1/2 n plus 1. You can already see that in many ways this is exactly why you should just use Faulhaber's formula for this stuff, because it's a lot easier than doing all this brackets multiplying out that we're doing here. But there you go. I just wanted to show a way that you can discover it completely yourself without remembering a sort of the full Faulhaber's formula. But there you go. So multiply out the brackets for the n plus 1 to the power of 6. We'll get n to the power of 6 plus 6, n to the power of 5 plus 15, n to the power of 4 plus 20n cubed plus 15 n squared plus 6 n plus 1 minus 1. And then some of the brackets are going to start simplifying. So first dealing with the 15 over 30, that will become a minus 1/2. We'll have the n out the front for the moment. We could have the n plus 1, 2n plus 1. So that's a 2n squared. Sorry, did I say that wrong? Basically, those first two brackets multiplied together. And then the 3n squared plus 3n minus 1. We'll have the minus 20 over 4, which is just minus 5 n squared. And then we'll have the n squared plus 2n plus 1. We will have the minus 15 over 6 simplifying to become 5 over 2 n, and then we'll have the 2n squared plus 3n plus 1. We'll have minus 3 n squared plus n, and then we'll have the minus n. Okay, and apologies, a small cut there because I didn't want to make you waste time watching me just rewrite out all that same line of working from before, copied from the previous page. But moving on to the next line of working, which is going to involve a lot of simplifying. So maybe you wish that I didn't show this as well. But I like to show all the stages of work in here. Actually, saying that, okay, I'm going to lie. We've got to multiply two brackets, so two quadratics out together here. And nobody wants to watch me probably do that. So I am going to make take one liberty of simplifying that. Also, while I'm at it, 6n take away the n would only be a 5n. And the 1 take away 1 would be no ones. So the minus 1/2 n out the front, but then multiplying those quadratics together, we'll get a 6n to the power of 4 plus 15 n cubed plus 10 n squared, and then we'll also get a minus 1. So there you go. That saved a bit of effort there. Not loads, but it's something. It's something. We've also got the minus 5n squared multiplying out there, so it'll get us a minus 5n to the power of 4 minus 10n cubed minus 5n squared. We'll end up with actually we'll deal with the minus 5 over 2 in a bit, because we've got something less nice to deal with there. So actually no, what we could do, okay, I keep changing my mind here. I'll keep the half out the front, but I'll times by the 5n out the front. So minus 1/2 timesing by 5n will get us a 10n cubed, a 15n squared, and a 5n. And then we end up with minus 3n squared minus 3n, and we already dealt with that minus n that was on the end. Thank goodness. So therefore, what was the next thing I was going to do? I was basically going to factorize out a factor of 1/2 out of everything here, because I don't want to deal with fractions if I can. So 1/2 factored out of everything will get me a 2n to the power of 6 plus 12n to the power of 5 plus 30n to the power of 4 plus 40n to the power of 3 plus 30n squared plus 10n. and then we'll just end up with n rather than a half n, but then I'm going to multiply the brackets, so it's minus n times by all that stuff will get me a minus 6n to the power 5, minus 15n to the power 4, minus 10n cubed, and a minus n. Except it'll be a plus n, sorry, it'll be a plus n because it already was a minus. And then we've also going to get the, if I could speak English properly, the minus 5n to the power 4 becoming a minus 10n to the power 4, a minus 20n cubed, a minus 10n squared. That half has been factorized out, so we just need to make all those things negative. So negative 10n cubed, negative 15n squared, minus 5n, and then we've also got the last bits becoming double the size because we factorized the half out, so minus 6n squared minus 6n. And then close the brackets. So therefore, I am then just going to, what am I going to do? I'm going to simplify everything. My goodness, that will get me a half, lots of 2n to the power 6. It'll get me a 12, a minus 6, so therefore that's just 6n to the power 5. We have a 30n to the 4. We've got a minus 15n to the 4, so that means 15n to the 4 overall, becoming a 5n to the 4 at that stage. We've got 40n cubes. Minus a 10 of them will get me 30. Minus another 20 will get me 10. Minus another 10 will mean I end up with no n cubes, controversially. Moving on to the n squareds, we've got the 30n squared. We've got no n squareds over there. We've got minus 10n squared, so we've got 20. Minus 15, so we're down to 5. But then we're taking away 6, so we've got a minus n squared. And then with the n's, 10n. Plus n is 11n, but then we're taking away 5n and taking away 6n, which means we end up with no n's. So there we go, we've got that. And that means that we have found, of course, 6 lots of the series for r to the power 5, which now means that if we want the series for r to the power 5, it's just going to be that divided by 6 to get rid of that 1/6. So dividing that previous thing we had by 6, it was a 1/2 out the front, so now it's going to be 1/12 out the front, and then the same thing inside the brackets. So 2n to the power of 6 plus 6n to the power of 5 plus 5n to the power of 4 minus n squared. And the only thing left to do is basically factorize it. Now you can already tell instantly, of course, it's got a factor of n squared that you could take out of everything. So let's do that. So it's reducing the power of everything by 2. But then also, because it was a show that I made it, or proof that I made it, we already know that n plus 1 squared is going to be a factor. So to save time, I could just immediately jump to dividing by not just the n plus 1s individually, but n plus 1 all squared, which of course would be a n squared plus 2n plus 1. So therefore doing the algebra division with that. Now you can use whatever method you like. What am I going? I'm going to use the grid method because it takes slightly less writing out. Algebra long division, more formal, but you end up having to do a lot of repeat writing of stuff out, which is a bit annoying. So let's start off with the 2n to the power of 4, and we're dividing by, as I said, n squared 2n plus 1. So what are we going to get? We are going to get the fact that this would have to be a 2n squared, which means we've got a 4n to the power of 3, 2n squared, which means that in this diagonal we've got the cubes, so therefore we need a 6n cubed, so we need another 2n cubed, which means that therefore this thing here needs to be a 2n, so that's a 4n squared and a 2n. And therefore it means we now need how many n squareds in total? 5. We've already got 6, so we need a minus n squared. So therefore that means we have a minus 1. and minus 1 will get a minus 2n, which is good because we've got 2n minus 2n, which will get no n's, which we want overall, and minus 1 times 1 is minus 1, which is also what we want. So it is good because it means we've got a factor, which is what we're expecting, but it's therefore nice to confirm it. So therefore our series is 1/12 n squared n plus 1 all squared, because n plus 1 all squared was the n squared plus 2n plus 1. And then we are going to be left with 2n squared plus 2n minus 1. So there you go. That is the series formula for r to the power 5, written in factorized form. As you can see, this method does start to become an absolute chore to do if you want to do it for higher and higher powers. You can do it. It just takes longer and longer to do. But therefore, Faulhaber's formula, I've finally remembered how to say it correctly. Faulhaber's formula is a lot quicker to use to find those higher series powers. Brilliant. So that will do us for today. So if you enjoyed trying these questions out yourself, then please do subscribe to my channel, because I've got an entire series of Can We Do That videos, which all have their own respective Can We Do That some more videos, giving you the opportunity to try some questions yourself. Hope to see you in a future video. A link to the entire Can We Do That series is on the screen right now.